Hello everyone. This project is titled uh, Cavern Drone Camp. Its full form is Cave Autonomous Vehicle for Exploration, Reconnaissance, and Navigation. So we head into the problem statement, which is to design and build an autonomous drone for subterranean hazard mapping and exploration. The project background is that the cave exploration dangers, current solutions has limitations, and the need for autonomy. So, the subterranean environments are inherently hostile with unstable terrain, total darkness, and exposure to toxic gases like methane, carbon dioxide, and hydrogen sulfide. The existing robotic solutions are often tethered, limiting range, or only rely on GPS, which is unavailable underground. Human explorers face significant physical risks. A critical requirement exists for a fully autonomous system capable of navigating, mapping, and assessing atmospheric safety without direct human intervention or risk. So, the technical specifications include the requirements of MICS 5524 sensor, which is a gas detection module. It has a compact MEMS sensor for detection of reducing gases, which is essential for atmospheric safety monitoring in enclosed cave systems. The CCS81 sensor is used for air quality monitoring. It's ultra-low power digital gas sensor for monitoring indoor air quality, provides direct ppm readings for the assessment. Then the LiDAR module, which is for navigation and mapping, the primary sensor for SLAM, creates high fidelity 3D topographical models in total darkness. The tensegrity gauge, which is structural protection, it is a icosahedron tensegrity structure designed for collision tolerance, which distributes the impact forces to protect internal drone avionics. The key features include SLAM-based autonomy, tensegrity cage structure, and LiDAR dark mapping. So the technical feasibility is navigation and positioning. So the GPS denied environment requires onboard SLAM NVIDIA Jetson processors are capable of running computationally intensive LiDAR mapping algorithms in real time. Communication RF signals attenuate in rock. Solutions include fiber optic tethers, relay nodes, or fully autonomous operation with data offloading post mission. Sensor payload, power and endurance, and physical design. The operational and economical feasibility. So the operational strategy is deployment and retrieval. To keep humans in the loop, meaning that initial missions utilize pilot assist modes where the drone handles obstacle avoidance while the operator guides general direction. And safety protocols. So the estimated cost breakdown is the prototyping and frame will cost around 3,500. The LiDAR sensor will cost 7,000. Onboard computing 37,000 rupees. Secondary processing 8,000 rupees. So the total estimated hardware is around 55,500 rupees. So the project timeline includes research and design will go on for the first 2 to 3 months. Prototyping and integration will go on for the next 2 months. Control testing after that, and then field testing, which involves deployment in actual cave-like structures and final system validation. So the total estimated time taken for this is 11 to 16 months. The key success factors in this include software robustness. So the most important element is the reliability of SLAM and path planning algorithms. Any failure in this subsystem directly translates to the total loss of the asset in a GPS denied cave. Iterative testing. A phased approach is non-negotiable. Success depends on extensive validation in controlled environments before attempting complex subterranean missions, and it requires adequate funding, since high-quality sensors like LiDAR and onboard computing is essential. So the conclusion for this project is the project is an ambitious but fundamentally feasible undertaking, while the technical hurdles in the subterranean environments are significant, they are solvable with current engineering standards. It just requires mature technology, no critical blockers, and it has a high value impact. Thank you.